Have you ever wondered about the mystery that surrounds the gaseous state of matter? This might seem like a strange question, but consider this. Gases are all around us, filling the air we breathe, inflating our balloons, and even powering our cars. Yet, despite their omnipresence, they remain somewhat of an enigma. Today, we're setting off on a journey into the fascinating world of gases. We'll delve into the basic gas laws that govern their behavior, exploring concepts like pressure, volume, and temperature, and how they interrelate. We'll then venture into the realm of ideal gases, breaking down the equation of state that portrays their perfect world scenario. But no journey is complete without some bumps along the road. We'll also explore how real gases deviate from these ideal conditions, leading us to the concept of compressibility and the intriguing Vander Waals equation. Today we're going to unravel the secrets of the gaseous state of matter. So buckle up and let's get started. When we talk about gases, we have to consider the basic gas laws. These laws are the cornerstone of understanding how gases behave and interact with their environment. Let's dive right into them, shall we? First up, we have Boyle's law. Named after Robert Boyle, this law states that the pressure and volume of a gas have an inverse relationship when the temperature is held constant. In simpler terms, if you squeeze a gas into a smaller volume, its pressure goes up, and if you let it expand, its pressure goes down. Like a grumpy cat, gases don't like being squished. Next on our list is Charles's law, which can be attributed to Jacques Charles. It says that the volume of a gas is directly proportional to its absolute temperature, provided the pressure remains constant. This means that as you heat up a gas, it expands, and when you cool it down, it contracts. Think of it like a balloon on a hot summer day, expanding in the heat and then shrinking back down as the night cools. Last but certainly not least is Avogadro's law. Proposed by Amedeo Avogadro, this law tells us that equal volumes of all gases, at the same temperature and pressure, contain the same number of molecules. It's like having different types of fruit, say apples, oranges, and bananas, but having the same number in each fruit bowl. Why are these laws important, you ask? Well, they allow us to predict how a gas will behave under different conditions. If you know the initial pressure, volume, and temperature of a gas, you can use these laws to predict what will happen if you change any of those variables. This is incredibly useful in a wide range of fields from engineering to medicine and even cooking. These laws lay the foundation for understanding the complex behavior of gases. And remember, gases may be invisible, but their impact is certainly not. They're all around us, and understanding them is key to making sense of the world. So stay curious and keep exploring. Now let's dive into the world of ideal gases. Ideal gases are a fascinating concept, the perfect inhabitants of a physicist's dream world. They exist only in theory, with no real-world gas fitting the bill completely. But why are they so important? Well, they simplify our understanding of the behavior of gases under varying conditions of temperature, pressure, and volume. The equation of state for an ideal gas is a simple mathematical relationship, often called the ideal gas law. It's stated as PV equals nRT, where P is the pressure of the gas, V is the volume it occupies, N is the number of moles of the gas, R is the universal gas constant, and T is the absolute temperature. This equation is the cornerstone of our understanding of gases, providing a handy way to predict how a gas will behave under different conditions. But to make things simpler, some assumptions are made about ideal gases. First, we assume that the gas consists of a large number of identical particles that are in constant chaotic motion. Second, we assume that the volume occupied by the gas particles themselves is negligible compared to the total volume of the gas. And third, we assume that the gas particles do not exert any forces on each other, except during collisions, which are perfectly elastic. These assumptions may seem a touch unrealistic, and indeed they are. But they allow us to understand the basic behavior of gases in a simple, intuitive way. And while they may not be entirely accurate, they are close enough to give us a useful starting point for understanding real gases. But of course, the world isn't as simple as our ideal gas model would suggest. Real gases often deviate from the behaviors predicted by the ideal gas law, due to factors like intermolecular forces and the finite size of gas particles. While ideal gases are a helpful concept, they are not entirely accurate, as real gases often deviate from these ideals. So what happens when gases don't behave ideally? Well, in the real world, gases often deviate from the ideal gas law. This is because the ideal gas law assumes that gas particles do not interact with each other and that they occupy zero volume. But in reality, gas particles do indeed interact, and they do take up space. So we need a better way to describe the behavior of real gases. This is where the concept of the compressibility factor comes into play. The compressibility factor, denoted as Z, is a measure of how much a real gas deviates from ideal gas behavior. It's calculated by comparing the molar volume of a real gas to the molar volume of an ideal gas at the same temperature and pressure. If a gas behaves ideally, its compressibility factor would be 1, but if the gas deviates from ideal behavior, the compressibility factor will be either greater or less than 1. Now, why is the compressibility factor important? Well, it helps us understand the behavior of real gases. By knowing the compressibility factor of a gas, we can predict how it will behave under different conditions. For example, we can predict how much a gas will compress or expand when the pressure is changed. This is incredibly useful in many fields, from engineering to meteorology, but the compressibility factor isn't a magic bullet. It doesn't perfectly describe the behavior of all gases at all conditions. For example, it doesn't account for the attractive forces between gas particles or the volume they occupy. But it does bring us closer to understanding the true nature of gases. In our next scene, we'll delve deeper into the world of real gases, exploring the van der Waals equation and critical constants. These concepts will help us further understand why gases deviate from ideal behavior and how we can better predict their behavior. The compressibility factor brings us closer to understanding the true nature of gases. Stay tuned as we continue our journey into the enigmatic world of gases. To further refine our understanding, we turn to the van der Waals equation. Now, we've learned that gases don't always behave like the ideal model predicts. That's where Dutch physicist Johannes Diederik van der Waals comes in. He proposed an equation in the late 19th century to account for these deviations, aptly named the van der Waals equation. The van der Waals equation is a modification of the ideal gas law that takes into account the finite size of gas molecules and the intermolecular attractions between them. It looks like this: P plus ANV squared asterisk Vm equals sign nRT, where P is pressure, V is volume, N is the number of moles of the gas, R is the gas constant, and T is temperature. The A and B are van der Waals constants that are specific to each gas. Let's break it down a bit. The term ANV squared accounts for the intermolecular attractions. It corrects the pressure of the gas, increasing it due to the fact that these attractions effectively reduce the pressure exerted by the gas on the walls of the container. On the other hand, NB represents the volume occupied by the gas molecules themselves. It corrects the volume of the gas, reducing it because some of that volume is taken up by the gas molecules. Now, let's talk about critical constants. These are properties of gases under specific conditions, namely critical temperature, critical pressure, and critical volume. These constants help us understand the point at which a gas transitions to a liquid, known as the critical point. The critical constants are directly related to the van der Waals constants. For a given gas, the critical temperature is equal to 8 times A divided by 27 Br. The critical pressure is A divided by 27 B squared, and the critical volume is 3 times B. With the van der Waals equation and critical constants, we can better predict and understand the behavior of real gases. We've traveled from the basic gas laws to the complexities of real gases. We've explored how these invisible particles follow certain rules, like the Boyle's, Charles, and Avogadro's laws. These laws form the foundation for understanding the ideal gas equation, a theoretical model that works perfectly under ideal conditions. But nothing is truly ideal, isn't it? That's when we delved into the deviations and compressibility factors, seeing how real gases diverge from the ideal, and how their behavior changes under varying pressures and temperatures. Remember our friend Vander? He came to the rescue with his equation for real gases, which took into account the finite size of gas molecules and the intermolecular forces between them. This led us to the concept of critical constants, the unique values of temperature, pressure, and volume where a gas can coexist with its liquid state. So, the next time you're contemplating the mysteries of the universe, remember the fascinating world of gases. Subscribe for more because you won't find me later.